Good morning, everybody. It's really to host this event. Thanks to Sibashish and his team to really take it up and then have this program in IMSC, because it is something that every institute doing science, particularly physics, is organizing this program, because it is a year or moment to celebrate, to sort of not only celebrate the kind of achievements that scientists have done in the context of quantum mechanics and that followed many other sciences. And it's very special for us because Niels Bohr visited us actually long ago, and he was instrumental to set up this institute. And there is a story behind it. I think you will hear from one of the speakers, teachers actually in this audience. Okay, so there is a history behind it that this institute was actually sort of set up with an advice of eminent scientist who contributed to quantum mechanics, father of quantum mechanics, Niels Bohr. So I take a lot of pride to say that I work in this institute, who actually have a big role in this. And we all, as scientists, have actually sort of contributed or also used or also benefited from quantum mechanics. And I think it's important that we should have one event of this kind, not only to update ourselves, and also to hear from people who contributed, particularly from our institute, from our country. And that's why this meeting has been sort of organized. And I see a lot of my teachers also here who taught me physics in this institute, and I managed to get some of those actually, like Professor Sackman, to get here. So I want to thank him particularly for agreeing to come here and actually start this program. So again, welcome to all of you for this nice event. And I think there will be more people joining. Right now there are not too many people. I expect more students from our institute to join, and also from organizations. So enjoy the stay here. As he said, there are a lot of talks, updating what's happening in quantum mechanics. Okay, so quantum mechanics, as you know, belongs to everybody, so nobody can claim that it is my topic or your topic. So I think we'll all benefit from the set of lectures here. Thank you again for joining me for celebrating this 100 years of quantum mechanics. Welcome again. Thanks.
Okay, so let me now invite Professor R. Simon to talk about quantum mechanics, about his work a little bit, and also about the institute.
Thank you, Sibashish, and I also want to thank Professor Ravindran for inviting me to come here today. It's very appropriate that this institute conducts this program in India as we celebrate 100 years of quantum mechanics. In fact, unlike many sciences, quantum theory is not an American science. This is the first remark I would like to make. I would like to argue that it's at least it's European science or Euro-Indo science. So I just wanted to bring for the younger students' attention the role India has played in the initial stages of quantum theory. I have in mind particularly Satyendranath Bose. Last year in Kolkata they celebrated the 100th anniversary of 1924 when Bose published his seminal paper. So I want to start from there. I wanted to go to that meeting, but somehow that did not happen. So Professor Guru Prasad really wanted me to go there. So some of these remarks are remarks I would have made there in any case. But I think it's significant that I thought I will make these remarks anyway. So let's take the date on which Einstein received a letter from S.N. Bose. I think the very popular rendering in some places can give a feeling that Bose became Bose because Einstein was very gracious. I think I would like to say that argue that that's not really entirely true. So what would have been Einstein's reaction when he received Bose's letter? To understand that, you have to go nearly 20 years back. So 1905, Einstein did many things, and the first thing that he did in that miraculous year was to write a paper, which now we call the Light-Konda paper. So it's a very beautiful paper. I think I will encourage all young people to read that paper. Very beautiful and written in a very, very simple manner. So he argues from thermodynamics that light, black body radiation of a particular frequency in the high frequency range, I would want to remind for you, black body radiation people analyze in the high frequency range, there it is called the Wien's law, and the low frequency range, there it is called the Rayleigh-Jeans limits. These were known earlier, and in 1900, Planck did a fantastic extrapolation of these things using his expertise in entropy. He studied the volume dependence of entropy to interpolate, and that's how he got the Planck's law. And then he also gave a kind of derivation of Planck's law. So this is where it starts. And Einstein takes the Wien limit of Planck's law. So I think the important thing I want to underline is Einstein really did not use Planck's law in that 1905 paper. He takes the Wien limit of Planck's law and studies its entropy dependence as a function of volume, and then says light behaves as if, and this as if he uses later on two occasions, in 1909 and 1916. So light behaves as if it consisted of packets of identical, indistinguishable particulate objects. Okay, this later on picked up the name Light-Konda. And then as an example of this consequence of what he was saying, he gave this so-called photoelectric equation. Okay, and this photoelectric equation later on was verified. Millikan says it took 15 years finally to validate Einstein's theory, because I think according to Millikan, he started with the idea of disproving him. I think that this Einstein's theory was viewed as madness in those days by including people like Planck. Anyway, so this is Einstein's first attack on Planck's law. He returns to it in 1909 and then analyzes the energy fluctuation of black body radiation, and it's okay. It's fine, yeah. Says it consists of particle kind of behavior at the Vn end and wave kind of behavior at the Rayleigh-Jeans end. Low frequency light, Planck's law behaves like waves in low frequency and like particles in high frequency. So this is the first formulation of wave-particle duality, but this time for radiation only. Again he returns to it in 1916, where he introduces these, the AB coefficients, which students should be familiar from their high school education, and he introduces the notion of stimulated radiation, which is the basis of lasers and masers. Then he gives a derivation of Planck's law, making certain hypotheses. So Einstein always wanted to give a full derivation of Planck's law. A full derivation of Planck's law in a real sense did not exist until 1924. So he was working on a full derivation of Planck's law, and here comes a letter from a young person in some corner of India, where the letter says, "We are all your students. I am your student, even though not by your direct teaching, but we are all your students through your papers and lectures," kind of thing. Now, so the letter says that Bose is a student of Einstein, but the manuscript has entirely something else. You know, Einstein has been working on an issue for 20 years, and here is an Indian physicist who has actually solved the problem, what Einstein wanted to do, or what Einstein could not do for 20 years, Bose had solved that problem. That is why he immediately translated it and had it published with this endorsement that this is a very important step forward. Because Einstein was all set, since he missed this boat with respect to radiation, he immediately applied it to molecules. And with his brilliance, he arrived at the condensation, Bose condensation, or Bose-Einstein condensation. So this is the contribution of Bose, that one paper. Abraham Price says that is the last and the fourth and last pillar of old quantum theory. So this is, now by 1924, quantum mechanics had become inevitable. That is why many people developed quantum theory in 1925 from very different directions. So it would have happened. Now another important contribution to in a theoretical physics institute we don't appreciate, another important, I should tell you what is the most important contribution of Bose. See, people had no idea how to do counting of identical indistinguishable particles in quantum mechanics. Nobody had any idea. Even though Bose, in a later occasion when he was interviewed, he said he did what Boltzmann would have done, but what he did was not what Boltzmann would have done. The counting that he did is something that he alone could have done. You know, this indistinguishability, the effect of indistinguishability, I think it's brought about in a Tamil movie comedy. I think it's a very effective illustration of that. So I just want to, I know some of these people who are visiting here may not understand Tamil, but I think you can always find somebody in this room during the next couple of days who will understand what I'm saying. See, this is this banana comedy. So the idea is that the one comedian, the bigger comedian, sends the smaller comedian to buy 2 bananas, gives money to buy a banana. And that fellow buys banana, but he actually gobbles one and comes and gives the one to him. So he asked, how many bananas did you buy? 2. But here is one, where is the other? He says, no, this is the other one. Okay? So which is the first one, which is the other? When the bananas are indistinguishable, it's a very effective comedy. So I think this is in a big way, I think it illustrates the... No, I really want people to see that clipping of the comedy. Well, if I had the resources, I would have maybe brought the clipping, but I don't have. Idanga adu. Yeah. Now, I think people will find out. It's sufficiently interesting. I think people should make the effort. Now, the second contribution from India is from C.V. Raman. These very early days, I mean, we don't, I think we theoreticians don't appreciate its importance, but it's one of the, I think it's not, Raman is not just a Nobel Prize discovery, I think it's among the Nobel Prize discoveries also, it tops in the list. So he did his work in, I think it's 28, he got the 30 Nobel Prize. So within 2 years, which I think is probably one of the shortest duration between work and its recognition by the Nobel Committee. See, I think Raman should be probably one of the most frequently used adjectives in science publications. By that I mean Raman effect, Raman activity, Raman transitions, and so on. We theoretical physicists, we don't probably use it much, but if you go to chemists or molecular biology, this is a big deal. The third one, so 24, 28, 31, Chandrasekhar did that big discovery, that is quantum theory of the large. Very important quantum theory of the large, Chandrasekhar limit is 1931. So that's also from India. I think even though Bose did not get a Nobel Prize, but I think the community has been kind of fair to him, but even the condensation is called Bose condensation because Bose-Einstein is just too long, so people call it Bose condensation, which I think is a very good thing. He owns half of the particles. And because I am talking this in this institute, and there's one more person I have to talk about, because all these people are people I have not met. They lived a little much earlier in time. That is Professor Sudarshan, who was the director of this institute. I said for Bose, the kind of society has been kind. Sudarshan felt that with, I think with reasonable cost, some level of justification, he felt that his thing was, he has also made very important contributions at the really cutting edge level. He felt that his work has been ignored. The first time he thought it was ignored. The second time, which is 2005, he even thought that it has been stolen. I think people will realize that he famously said, in a very metaphoric way, give unto Glauber only what is Glauber's. Okay? So, because I have already quoted a movie, I just want to quote one more movie thing. So I was wondering what would have been Sudarshan's reaction. Many people many of us have met him, have been with him. So I was wondering what would have been his reaction when he watched the Nobel presentation to Glauber. Again, I could not resist feeling another comedy scene. This is, I think it's in the one Rajini movie. And Sendil's wedding, Rajini and all, they go. On the way, Sendil falls into a ditch in a very dirty water, so his dress gets soiled. So on Sendil's comedian's request, Rajini gives his dress to him, his suit to him. And then at least 2-3 occasions when somebody says, who is the bridegroom? And Rajini will say the comedian is the bridegroom. But the dress he is wearing is mine. Okay? So I thought Sudarshan could have been another, well anyway, that he made very important contributions to quantum theory, there is no doubt. We are talking about whether he was recognized with the Nobel Prize or not. And I feel there was some element of justification in his expectation and claim. So I think when he saw that plank being honored, he would have probably thought that the bridegroom may be Glauber, but the suit he is wearing is definitely mine. Okay, so I don't have anything, I don't have a prepared speech. I think we have far exceeded my limit, the limit given to me. Once again, I thank you for making it possible for me to hold a mic after 8 years. Thank you, Ravi, for it. And I think we have a wonderful set of speakers, so we have a big treat on the way. I think it's a worthy celebration, and the Institute is probably the best place to do this celebration. Thank you very much.
Very Sayantan. So, Sayantan will have to chair,
He's not around, is it?
He's not there.
Maybe I'll just ask.
Sure. Okay.
So who is the first speaker actually?
Guru Prasad Kaur. Guru Prasad Kaur. Guru Prasad Kaur is the first speaker. And second speaker is Subhash Jyoti.
Yeah. Okay. No, no. So, let me thank Professor Simon for his reminiscence about his feeling about quantum mechanics, and let us begin this session with Professor Guru Prasad, who is going to talk about understanding the non-local and contextual characters of quantum mechanics. So let me welcome. We have two talks today, and 2 talks in the morning, and this is his first talk.
How it works. Sorry. Yeah. Hello. I'm audible? So, first let me thank the organizer, especially Professor Ravindran, Shivashish, and it is nice to see Professor Simon, Professor Bhaskaran, Professor Govinda Raju after a long time. Professor Bhaskaran is there also. So I will be focusing on something which came much later, what Professor Simon told. So it's about, and especially I have been requested to talk about this non-local and contextual character. Most possibly Shivashish also asked to tell something about collapse postulate, but I could not cover collapse postulate in these talks because that is a separate area which needs a different separate talk. So you know that these 3 people, Aspect, Clauser and Zeilinger, they got the Nobel Prize because in some sense they could prove by their experiments that finally Einstein was wrong. Einstein is wrong in a particular way that I am going to describe. And there is a famous quotation from John Bell that Bohr was inconsistent, unclear, willfully obscure, but finally right. Whereas Einstein was consistent, clear, down to earth. Down to earth means the way we think about the world, he used to think in that way. But finally wrong. So this is the thing that I am going to cover in this talk. So I start from brief description of quantum mechanics. So you know that quantum mechanics has to be described in a Hilbert space, and state is unit vector in that space. I am not talking about density matrix because I don't need the description of a state. And observable is Hermitian operator, which can be written in this form. I mean, it's a spectral representation. That means AIs are the eigenvalues, phi's are the eigenfunctions, and its spectral representation is like this, and where the summation over these orthonormal projectors is identity. So sometimes in a state of telling this observable, I can just tell that my measurement is summation over some orthonormal projection of orthogonal projection operator, summation over pi is equal to identity. This is my measurement, and we will be interested in some maybe ith results. Now measurement results, there is sometimes it is not told in the postulate. Measurement result is one of the eigenvalues. So it should be spoken as a postulate. Now how quantum mechanics works? So if you prepare the same state, psi, like many copies of psi, then there is a rule which is called Born's probability rule, which tells that if you prepare the same state and you measure these observables, say summation over pi is equal to identity, then probability of getting the ith result is given by the expectation value of these projectors, corresponding ith projectors. and finally if you write Pi as phi I, then you get this probability rule. And finally, if you get in the measurement, if you get the ith result, then whatever the initial state is, the final state is phi I, that means corresponding eigen state. Now this is quantum mechanics. So now let us see how this Copenhagen interpretation tells about measurements. So we consider a quantum state which is the up eigenstate of sigma z, and if this is my initial state get 0, then if you measure sigma z, you know certainly that your measurement results will be up. That means probability is equal to 1. So you can tell it's a reality of the particle that sigma j, I will always get sigma z is equal to 1 if my initial state is get 0. But instead of measuring sigma z, if you measure sigma x on the same state, then half of the times you get up and half of the times you get down, and also the state collapses to up eigenstate of sigma x and down eigenstate of sigma x. Now if you ask the question that before my measurement, what about sigma x? Then this Copenhagen interpretation will tell that before the measurement of sigma x has no value. Value will appear through the measurement. So individual particle does not have a definite spin value along x. Measurements only creates the result. And this is what Einstein could not accept. Einstein used to think that measurement reveals predetermined result. I mean, there is something there, we only reveal those values through our measurement. Like we don't think that thermometer creates our temperature. We think that temperature is already there, thermometer only reveals it. So see, if you consider two pictures, see how Einstein used to think. So as I told you, quantum mechanics, if you prepare this state, then for sigma x, half of the times it is up, half of the times it is down, if you perform the measurement of sigma x. Now let us have an alternative picture. We tell that, okay, your quantum state it gets 0, but I can designate the state in this way that each individual particle has a definite value for sigma z, which is equal to 1, but they have a definite value for sigma x also. But nature is such that if you prepare this state, many copies of this state, nature is such that half of the times sigma x is equal to plus 1. I mean, if you prepare many particles in this state, then half of the time sigma x is equal to plus 1 and half of the time sigma x is equal to minus 1. Then let me ask you, can any measurement tells that this picture is wrong? Because the same statistics you will get. Even if you consider that not only sigma z, even for individual particles, sigma x has also a definite values, but nature is such that if you prepare this state, many copies of this state, half of the time, half of the particle has sigma x is equal to plus 1, half of the time, half of the particles, for half of the particles sigma x is equal to plus 1. But this goes against Copenhagen interpretation. They will tell no, in this state sigma x cannot have definite value, only measurements will create one of the value which may be either up or down. But you will not see any, that measurement can discriminate between these two pictures. Bohr and Heisenberg and their co-workers like Pauli, Jordan used to believe that such picture cannot exist. It was their belief. And von Neumann in 1932 even claimed to have proved that dispersion-free state is not possible, like this picture will never exist, as if He has proved it by some theorems which we will discuss. Einstein for some time challenged like in 1927 there was a big debate between Bohr's camp and Einstein. And Einstein for some time challenged the impossibility of joint measurement of some observable like position and momentum, but at one point of time he accepted the impossibility imposed by nature. That is, he accepted that okay, there may be some observable whose joint measurement may not be allowed by nature. But never accepted the impossibility of quantum system having definite values for observable to be revealed in measurement. That means Einstein still used to think that this kind of picture is possible. And there is very extreme kind of a statement from Pascal Jordan. Observation not only disturb what has to be measured, they produce it. We compel the electron to take a definite position. We ourselves produce the measurement of result. It's a very subjective kind of a statement they made. And Niels Bohr told that it is wrong to think that the task of physics is to find out how nature is. Physics concerns what we say about nature, but I am not going into this philosophical debate. But finally Einstein's response was God does not play dice with the universe. And some people tell that Bohr used to tell that Einstein should not decide what God should play. So let us look at the von Neumann's theorem, where he claimed to have proved that quantum state is the final state. You cannot go beyond that. So the picture where I show you that individual particle can have definite value for both sigma x and sigma z, this kind of picture cannot exist because quantum state is the final thing. He claimed to have proved it by giving these three assumptions, that some expectation functional which acting on identity gives you 1, and this is linearity, some kind of linearity of expectation functional, and I have put it in red because of some reason that will be revealed. Arabia Hermitian operators, and if you find the expectation value on projectors, it must be positive, and finally you know this gives you probability. Von Neumann then, using these three assumptions, he proved that any expectation functional that you can define on Hermitian operators, they comes from a quantum state. So other than quantum state, even if you start from some general assumption, finally you land up to quantum state only. So, and quantum state, you know, it cannot be dispersion free. Like ket 0. For ket 0, sigma z may be is equal to 1, but sigma x cannot be either 1 or minus 1. So quantum state is the only solution establishing the impossibility of dispersion free state. So the picture that I put on the right side, that is discarded. And come to Einstein, how Einstein used to think. Quantum mechanics is a probabilistic theory, but Einstein used to think any fundamental theory of nature should have these two properties. It should be non-probabilistic. He used to tell this term, this realistic, but sometimes he used to mean it to be deterministic. And another thing is, local. Local means there should be no action at a distance. And he used to believe that, as I told you, measurement does not create but reveals predetermined values for observables. And in 1935, EPR, Einstein, Podolsky and Rosen, using the idea of reality and locality, tried to show that quantum mechanics, if not inconsistent, it is, if not wrong, but it is complete. So this is the picture of quantum mechanics. So I have considered a maximally entangled state of 2 qubits, and it is a variant of singular states. And this state has nice property that if the particle are far apart, still if they measure along the same direction, if both measure sigma z or both measure sigma x, then results are completely correlated. If this fellow gets up, that fellow also gets up. If this fellow gets down, that fellow also gets down. This is not only for sigma z, this is also true for if both of them perform sigma x measurement. Now this is quantum picture. This is the quantum state. Now come to EPR picture. EPR picture tells that when the particle, let the particle are far apart, but both the particle has definite value for sigma z and sigma x, similarly for this particle. But the value are assigned in such a way, if here it is sigma z is equal to plus 1, it is also sigma z is equal to plus 1. If for the first particle sigma x is equal to minus 1, for the second particle also sigma x is equal to minus 1. So that if you assume that measurement only reveals predetermined values, then also you get the same kind of correlation, because you have, this is the EPR picture. But this may be Einstein's belief that particle has definite values which will be revealed in measurement. But what Einstein did in this EPR paper, it is something more. Actually, Einstein used this idea, locality and reality, that I told you. They proved that using these two ideas and considering a quantum correlation revealed by this singlet state, they claim to have proved that quantum mechanics is incomplete. And so using these two concepts, using these two concepts, they prove that sigma z and sigma x both are real. But they are proving that sigma z and sigma x both are real by using the idea that world obeys this locality condition and reality condition. I am not going in details to describe this EPR paper, but now we are telling us from these two assumptions, if you can conclude that sigma z and sigma x both are real, then what you can tell about quantum mechanics? You can tell that quantum mechanics may not be wrong, but quantum mechanics does not contain this truth that sigma z and sigma x both have definite values for a single particle. So in that way, quantum mechanics is not wrong, is not inconsistent, but incomplete. That means it does not contain a truth which can be derived by using locality and reality. Yeah, I have a little water. Thank you. Yeah. Now, so we know quantum mechanics, but how a more deeper theory can be constructed. So this is the thing that Bell started to think in this way. So let you consider an ensemble of a quantum state. So all the particles are in state psi, but maybe there are some other variables which we cannot control, which we cannot know. That is another variable, say lambda. And though we see that the particle has been prepared in the same state, actually if you consider the other variable which we have the power to control, in terms of that other variable, actually the state may be different. This is the main idea. So it is not a theory you are not going to construct. You are trying to tell that, see, von Neumann may not be the final answer. That means whether in principle you can construct a theory where every observable will have a definite value, but on the average it will obey quantum mechanics, because quantum mechanics is experimentally verified. So now psi and lambda decides the value of all observables. That means if you consider an observable A, then if you know psi and lambda, then you have a definite value for this observable, and from the postulate of quantum mechanics, measurement values only can be one of the eigenvalues. So there is a restriction on these values given by this hidden variable theory, which is so this value has to be one of the eigenvalue. And to be compatible with quantum mechanics, you have to average over these hidden variables. So there is a distribution of lambda, and if you integrate over mu lambda d lambda, you get the quantum things. So finally you have to reproduce the quantum mechanics, either in terms of average value of A or in terms of this Born probability rule, where these are probability functions. Now, this is a very powerful statement from J.S. Bell that von Neumann, he's talking about von Neumann's theorem. It's not just flawed, it's silly. Von Neumann claimed no to the impossibility of dispersion-free description. So, to understand that, we consider three observables, three Hermitian operators, say A plus B is equal to C. Then, if you consider the second condition put by von Neumann, this linearity of expectation functional, then von Neumann's claim is that this should be satisfied for any theory S. If you consider any theory, maybe it may be quantum theory, it may be classical theory, it may be some hypothetical theory, whatever it is, this condition has to be obeyed as being the state of the theory. Now, if you come to the psi lambda theory, which we just described, then actually what it boils down to, if you consider this equation, then it boils down to that eigenvalue of A plus some eigenvalue of A, some eigenvalue of B is equal to some eigenvalue of C. So it boils down to von Neumann's second condition, which I put in red, that boils down to, for a theory which gives definite value to observable, it boils down to that this condition has to be satisfied. But this is not a verifiable condition, because ABC may not commute. You cannot have a simultaneous measurement of ABC. What you can verify is quantum. That means average value of A plus average value of B is equal to average value of C. That you can verify. But this thing you cannot verify. And actually what von Neumann is doing is very silly. See how. So you use this equation. Yeah. I'll come even stronger statement. So you use this equation. So in place of these three, you put this, as if hidden variable theory is possible, you put these equations, and finally this. Finally, value of A, value of B minus value of C in the state psi lambda into mu psi lambda, that means probability distribution of lambda, d lambda is equal to 0. Then from here, can you put this condition is equal to 0? This is like saying integration of fx dx is equal to 0 implies fx is equal to 0, where you have not mentioned that fx is non-negative function. That's why it is silly. And now I am coming to some quotation from Bale to see. Yet the von Neumann proof, if you actually come to grip with it, falls apart in your hands. There is nothing to it. It's not just flawed, it's silly. When you translate his assumption into terms of physical disposition, they are nonsense. Even a stronger statement. You may quote me on that. The proof of von Neumann is not merely false but foolish. He made this statement in an interview in 1988. Actually, in von Neumann is trying to prove that hidden variable cannot exist. It reduces to, if you consider spin observable, it reduces to this condition, which is obviously impossible. But if you integrate over, put integration over this hidden variable state, it may it may be compatible with quantum mechanics, yes.
Wasn't this shown by Greta Hermann?
Yeah. Actually, Greta Hermann, possibly some German scientist, he actually,
She was a student of Heisenberg,
he was a student of
and then
Heisenberg.
moved to philosophy after the thesis.
Yeah, maybe in
And the
1935.
thesis was about this problem.
So you are correct that Greta Hermann, if you remember that I put the second condition in red, so that is the point of attack. And Greta Hermann objected this, put objection against this condition, but maybe von Neumann was a big mathematician and physicists were somehow convinced with his proof, so they didn't care about Greta Hermann's comment. Yeah, it is very important historical comment. Thank you. Now, J.S. Bell didn't stop there. He told that I can construct one. If you can construct a hidden variable theory, then this is the best thing that you can do. So you disprove the theorem in a very elegant way. So what you do for that? So this is I have written this quantum state in terms of density matrix in this form, because then this density matrix, every density matrix of a qubit can be associated with the points in Bloch sphere. So this is very beautiful representation, and in that way, if your state of polarization direction is n, and if you measure along some direction m, I mean you measure spin along some direction m, then probability for half result is very interesting. Half 1 plus n dot m, where this n dot m is just ordinary scalar product in R3, and for down result it is this, and if you want to find the average is just n dot m. So what you do, it is not exactly what Bell did. Bell actually for this hidden variable, he also used some other vector. Here it is a scalar, it is even simpler. It was done possibly by Beltramitti and Cassinelli. So what you can do, so you can tell that completed state is not just quantum state. Yeah, it has to be completed by adding some other variable, which is in this particular case is a scalar, just lambda, which can take value from minus half to plus half, and the distribution is uniform. And you give a rule. So you can give a rule like that if your state is n lambda, and if you are interested for some spin observable along the direction m, then the value of this spin is given by this formula, which is a sine function, and sine function is finally plus 1 or minus 1. So you are putting this rule by hand. I am trying to convince you that you are not constructing an alternative theory to quantum mechanics. You are telling that what von Neumann said, you can show that there is a mathematical model where for every state, every observable will have a definite value. We are trying to prove that. And this sine functions is 1 when x is greater than or equal to 0, and minus 1 for when x is negative. And interestingly, I have taken a case where n dot m is equal to negative. You have to consider another case where n dot m is positive. And finally, if you calculate this average, that means you finally integrate over rho lambda d lambda, you get the quantum result. So still, by giving definite values to all particles, all spin particles, telling that it has definite value for spin, all spin observables, still you can reproduce quantum mechanics on the average. So no measurements can tell that this is wrong. But now there is a question. So apparently it seems that Einstein was correct. At least for spin observable, if Einstein claims that, no, I believe that measurement only reveals predetermined result, then there is no experiment for qubits which tells that Einstein was wrong. But now come to a different question. Go to the higher dimension, maybe 3 onwards. Now consider any measurements. Measurements means, as I told you, some measurement in a basis, that means summation over pi is equal to identity, where pi may be one-dimensional projector on phi I. Now consider a measurement basis phi 1, phi 2, phi 3. But problem is, so this is the basis where outer product of phi 1 plus outer product of phi 2 plus outer product of phi 3 is equal to identity. Now, but being a 3-dimensional Hilbert space, you can consider another basis, which is pi 1 remains same, but these two, you consider, you choose a different basis phi 1, xi 2, xi 3, where xi 2 is equal to phi 2 plus phi 3 by root 2, and phi 3, xi 3 is equal to phi 2 plus minus phi 3 by root 2. That means you are considering a 2 orthogonal basis where one is common. Now, hidden variable theory would give a definite value to a projector or to a Hermitian operator. We are restricting ourselves to projector, and projector can have only 2 values, either 1 or 0. So any hidden variable theory, if it claims that it is consistent with quantum mechanics, then it has to give definite values to all the projectors, which can be either 0 and 1. Now a question arises in 3-dimensional onwards, which didn't arise for qubit. That is, this projector P1, that is common. It is in this measurement set as well as the other measurement set. Now the question is, are you going to give same value without caring in which measurement basis it appears? If you do, then it is called non-contextual value assignment or non-contextual hidden variable theory. And Bell as well as Koch and Specker in 1967, they could prove that quantum mechanics is, non-contextual hidden variable theory is inconsistent with quantum mechanics. Here there is a little bit blow to Einstein. Einstein was thinking everything will have definite value. Now the question comes that if you consider a projector which is in different measurement basis, then are you giving the same value or different value? Einstein was not alive around that time, so this question didn't arise to him. But this is a very important question. And as I told you, Bell and Koch and Specker could prove that non-contextual hidden variable theory cannot reproduce quantum mechanics. And there is a nice proof. So this is the condition, that in this case non-contextuality implies that this particular projector, in whichever set it appears, whichever measurement it appears, you don't care, you give the same value. Then actually in 1967, Koch and Specker could, using 107 projectors, could prove that it is inconsistent, it cannot reproduce quantum mechanics. But we are lucky that in 1996, Adam Cavallo gave a nice proof in 4th dimension. 4th dimension, even not only 4th dimension real Hilbert space, in R4, he considered 18 vectors, and put these rules of non-contextuality, that every projector, I have, in a state of writing value on the projector, I have written it value on the vectors. So it can be either 0 or 1 according to hidden variable theory, and some of them should be 1 because they are mutually exclusive in a particular measurement. And using these 18 vectors, Adam Cavallo has a 9 orthogonal set, and each projector has appeared twice. This phi 1 has appeared twice. This phi 2 will also appear twice somewhere here. Similarly, you can see every projector has appeared twice, and you have given a definite value which can be either 0 or 1. Now, and all these are orthogonal set. This phi 1, phi 2, phi 3, phi 4, phi 1, phi 5, phi 6, phi 8. So you have to check. So they are orthogonal set. Now, if there is non-contextual hidden variable theory, then all these 9 conditions has to be satisfied. But if you add them, you get a contradiction. Because here all these things has appeared twice, which can have value either 0 or 1. So it would be even on the left hand side, but odd on the right hand side. So it doesn't work. It shows that non-contextual hidden variable theory in general cannot reproduce quantum mechanics. Now we are coming to John Bell's theorem. So what we saw, that Einstein in 1935 claimed to have proved that quantum mechanics is incomplete. Which condition he used? Locality and reality. Now Bell is putting a different questions. He is telling first, okay, Einstein is using locality and reality, but let us first check whether quantum mechanics is compatible with the conjunction of these two ideas. Whether quantum mechanics is compatible with locality plus reality, because both the assumptions were used by Einstein. And Bell found that they are in opposition. Local realistic theory cannot reproduce quantum results, quantum statistics. So when Einstein used to believe that nature obeys local realistic condition, Bell put forward a different question: is quantum mechanics compatible with local realism? Bell's theorem tells that quantum mechanics violates local realistic theory. Now I am putting a very simple proof. It was proved in 1981 by David Marmin, and a modified version of this proof was given by some person that will come, and I even simplified them. So it is a very simple setup. So there is a middle, there is a source. If you push some button, there will be 2 particles will be produced. One will go to the left and the other will go to the right, and there is some Alice Bob who can measure on this particle. There are 3 possible measurements on each side. This is measurement 1, measurement 2, measurement 3, similarly on the side, and measurement result, if it is up, then red light glow, and if it is down, then green light glow in this. And so 3 possible settings on both sides. Outcomes are +1 and -1 for all of them. Choice of setting on each side are completely random. This is very important. This choice making by Alice and Bob on the side, they can choose according to their own will, whether they will perform the measurement of 1 or 2 or 3. One of the measurement has to be performed. They can choose it freely, independently. Sometimes it is called free will, which cannot be proved, but which we assume. And statistics will be collected by running the experiment many times. So what happens? So each time the particle source, there is a button which is pushed, 2 particles goes to Alice and Bob, and Alice choose either one of the 1, 2, 3, and similarly Bob choose 1, 2, 3. So, so how many pair of measurements are there? I think 9 pairs of measurements, like 1, 1, 1, 2, 1, 3, similarly 2, 1, 2, 2, 2, 3. And the statistics will be collected for all these measurement results, and then the statistics generated from the measurement satisfy to. Now, many times this measurements has been repeated, and statistics, all these statistics has been collected, and after collecting it, we see there are 2 features. First feature is for same measurements, that means 1, 1, 2, 2, 3, 3. In this case, the same measurement, the outcomes are always same. This is one feature of the statistics that have been collected. Second feature is the property of having same outcome on both sides for different measurement setup, that means 1, 2, 1, 3, 2, 3, for this kind of measurements. The probability of having same outcome on both sides for different measurement is 1/4. These are the two features of the statistics. And now we will check whether these two properties can be compatible with local realistic idea. And as I told you that and David Marvin did it in 1981, when developed by L. Macone in 2013. Possibly I have a little bit even simplified. So based here on these two properties of these statistics are in contradiction with the following assumption: locality, reality, free will to choose among the settings. If you have these three conditions, actually Bell never mentioned about this condition because we assumed it that we have free will. We can choose any one of the measurement we want to choose. And see, now if you assume that for each particle or for each pair, definite values for all these three observables on each side can be given definite values, then in how many ways the values can be given? For first particle, values can be given in this way. See, there are 8 possibilities. Maybe all are +1. First two are +1, second row is -1. In this way, in 8 possible ways. Similarly, for the second particle, there are 8 possible ways. So in totality, for a pair of particle, how many possibilities are there? I am asking the students. How many possibilities are there that you can assign definite value to the pair? Yes? 64. Yes. Now, among the 64, let us choose these one. Say for a pair of particle, plus 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 here, and here it is second one, plus plus minus. Will this work? Go to the condition, look at the first condition, and I am asking you whether plus 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 and plus plus minus will work. It will not, because if both of them measures A3, this is A3 and the third measurement, then results has to be same. This will not be satisfied if this assignment is taken plus 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 and plus plus minus. So finally, so there are 64 possibilities, but finally, how many will be there? Finally, 8 will be there. Because for the first condition, if you take here plus plus plus, for the second particle it is also plus plus plus. If for the first particle it is plus plus minus, for the second particle it has to be plus plus minus, because it has to satisfy the first condition. Look at the first condition. If they choose the same measurement, their result has to be same. So finally there are only 8 possibilities. These are the 8 possibilities. So these are the 8 possibilities. Now, the second condition, if you remember, that if they choose different setup, then probability of having the same results will be 1/4. So there are 8 possibilities, and you can think of that this first possibilities appears with probability P1, second possibilities appear with probability P2. In this way, P1, P2, P2 to P8, and sum of this P1 to P8 is equal to 1. Now, if you calculate that measurement choice is 1 and 2, so what is the probability that the results are same? You will see the contribution will come to from first, second, seventh and 8th. So it will be P1 plus P2 plus P7 plus P8. In this way you can calculate and you can sum these 3, and finally you get this is equal to 1 plus 2P1 plus P8. And from this you can conclude that sum of this thing is greater than or equal to 1. So don't think that I am adding probability and it is going beyond 1, because this is not mutually exclusive probabilities. It is not probabilities of mutually exclusive events. So this probability can go, of course can go, theoretically it can go beyond 1. But okay, so we get this inequality, that this inequality has to be satisfied if they chose this setup 1, 2, setup 2, 3 and setup 1, 3. But now come to the first condition. So it is 1/4. So if you put 1/4, 1/4, 1/4, this 3/4. Where local realistic theory tells that it should be greater than or equal to 1. Now the question comes, the correlation that I am talking about, is it feasible? These are good questions. And there is a quantum state against this variant of singlet state, and there are 3 possible quantum settings from which you will get, it will satisfy the first condition as well as the second condition. So, in reality, you have a quantum state and 3 possible measurements on this side, 3 possible measurements on this side, which can have these statistics. So, how much time do I have?
20 minutes. 20 minutes.
20 minutes, okay, thank you. Yeah. But people talk about Bell's inequality, and when I started maybe in 90s, I started reading Bell's thing, so it is always Bell's inequality. But I took, it took some time to understand Bell's inequality. I was trying to understand Bell's inequality, and it took maybe 6-7 months to understand it properly. But nowadays, because of so many discoveries in 90s and still now, that it's easier for you to understand it. So we are not going in a classical way to understand Bell's theorem, but we are putting a very interesting game. So the game is something like this. These values, there is Bob, they are put in 2 different rooms, and there is a game something like this, that Alice will be asked a question from this pair, A1 or A2. But questions are not it is not some rational question that they have to think and give answer, not that. Answer can be only +1 or -1. And here it is A1, A2, B1, B2, so they will be given pair of questions. So how many possible pairs are there? 4. A1, B1, A1, B2, A2, B1, A2, B2. There are 4 possibilities. Now they will be kept in a separate room, and after the game starts, they are not allowed to use their mobile. That means they cannot communicate. That means if Alice gets a particular question, she does not know which question Bob has got, and similarly for Bob. And what is the winning when they will win this game? The winning condition is given by this thing. So this game will be repeated many times, maybe 1,000 times, and now all their answer will be collected to a room, and their winning condition is, in those cases where this fellow gets A1, this fellow gets B1, so 1/4 of the times these 2 people will get this set of questions, A1, B1. In all those cases, their product of their answer has to be +1. And similarly for A1, B2, similarly for A2, B1. So individual answer does not matter. What has to be satisfied? That their product of their answer has to satisfy this condition. And the last one, when in those 1/4 cases where this fellow gets A2 and this fellow gets B2, their product of their answer has to be -1. And you see, this condition is satisfied. If you take the average, it will be 4. But anyway, they have to satisfy this condition. Now my question is whether, so before the match starts, Alice and Bob can come together and they know all these winning condition and all these things. So they will decide some strategy so that they can win this game. And now the question is it possible to construct a strategy, because after the game starts, they cannot use their mobile, so they cannot communicate with each other. Can they win this game? And you will check that it is not possible, because if you consider a particular turn when Alice has decided that if question A1 comes my answer will be this. And for question A2, my answer will be this, which can be either +1 or -1. Similarly for Bob. Now they don't know which pair of the question, there are 4 possible pairs, which pair of the question is coming. So if they want to win, they have to win the game, they have to satisfy these conditions, they have to satisfy this winning condition in all cases. Now they have a particular answer, they have decided a particular answer, and this answer can depend only on the question, because Alice's answer for A1 cannot depend on the question given to Bob, because they are not allowed to communicate. Now, if they have to win this game, then their answer set has to satisfy all these 4 conditions. And it is not possible, because see, the answer of Alice for A1 has appeared twice. And similarly, all the terms has appeared twice. And if you take the product, left hand side it will be positive, right hand side it will be negative. So there is no deterministic strategy by which you can win this game. But you see that if they decide to answer in this fashion, that whatever question comes, we will answer 1. Both Alice and Bob decide. Then see, they can be successful in 75% cases, because they will satisfy the first 3 conditions. And Bayes' theorem is nothing but it tells that using local hidden variable theory or using local realistic condition, the highest winning probability is 75%. You cannot go beyond. And this is actually done by Bell in 1964. So it is just like earlier cases. If you assign definite values to this particle for 2 possible measurements, there was 3 possible measurements on each side. In Bell's inequality is 2 possible measurements on each side. And if you assume that definite values can be given, then for these 2 observable, there are 4 possibilities that you can give definite values: plus, 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 minus, minus, plus, minus, minus, and similarly for this particle. So as total, there are 16 possibilities, and using these 16 probabilities, I am not going in details. You can calculate these average values, and finally you can prove that these averages is restricted. This absolute value of this thing cannot go beyond 2. This is Bell's inequality. It's very simple. You can read from any books. But now I told you that from our common sense tells that if we play the games without communications, then at least with 75 probability we can be successful in this game. And I told you that according to Bayes' theorem, that is the highest by not only classical world, classical mechanics, but by any local realistic theory. Now we can prove it. So what we do, so this is Bayes' inequality, that's average of A1 B1, A1 B2, A2 B1 minus A2 B2 is bounded by 2. So what you can do, you can calculate this average in this way. So average of AI Bj is nothing but probability that AI is equal to Bj, because when AI is equal to Bj, product of their result is +1, because it can be either both -1 or both +1. And minus probability of AI is not equal to Bj, that means +1, -1, -1, +1, if you take the product it is -1. So you can express this average in terms of these 2 probabilities. And using this thing, you can rewrite this Bayes' inequality in this way. Probability of A1 B1, A1 B2, A1 is equal to B2, probability of A2 is equal to B1. Because if you remember the condition of winning condition of the game, in the first 3 cases their result has to be equal, so that their product of their answer is +1. And the last one, their results should be opposite, so that product of their results should be -1, if you remember the condition of this game. So, and each question may come 1/4 times, so if you multiply by 1/4, so this is the winning probability of this game. Winning probability of this game. But you have used Bell's inequality. That means you are obeying local realistic condition put forward by Einstein. And you see that probability of winning is restricted by 3/4. So you cannot go beyond 75%. So what our common sense tells from looking at the games, that is the final result, that is Bell's inequality. But quantum mechanics is not that much magical. Quantum mechanics tells that I have a state, again singlet state or any maximally entangled state. Here I have chosen the singlet state. And if you play a game by sharing a quantum state, quantum singlet state, and choose your measurement according to the question. Question means question is A1, A2 for Alice, B1, B2, Bob. So depending on the question, they can choose the measurement in such a way that, and when the result is up, they will tell my answer is +1. When the result is down, they will tell my answer is -1. In this way, by sharing quantum correlation, if they play this game, still they cannot win this game with 100% probability. But they can go up to 85%. So 10% advantage by quantum. And again, there is a theorem, that not theorem, there is some assumption and based on that assumption, it is some question, it is called information causality condition. They tells that no, again in nature this is the highest. You cannot go beyond 85%. And this is called correlation bound. Anyway. Now let me just tell you that one thing, that we should not confuse between relativity condition, that means no signaling condition, and Bell's locality condition. Actually Bell's inequality can be derived from a more general condition than determinism. Even if you tells that this probability at the lambda level is just factorized. It did not be deterministic, it may be stochastic. But at the lambda level is the probability of probability of getting a particular result on Alice side and Bob side. If they factorize, even if you can derive this Bell's inequality. But see, Bell's inequality is factorization, but if you come to no signaling condition tells that my probability of getting a particular result on this particle should not be influenced by choice of measurement on the other side. So no signaling condition does not imply that its probability has to be factorized. It tells that if you sum over B, then this probability of getting A does not depend on Y. That means does not depend on the choice of the measurement on the other side. If it depends, then it is signaling. You can send information instantaneously. So Bell locality condition implies no signaling condition, but not the other way around. And indeed, there is a correlation. This is called Popescu-Ehrlich correlation. Popescu-Ehrlich correlation. Actually, for that, this Bell quantity can be, so by local realistic theory, it is bounded by 2, but for this correlation, this Bell's quantity becomes 4. It varies even more. And with this correlation, you can win this game with 100% probability, because they see for first 3 cases, product of their measurement, product of the result is +1, and last case product is -1. So had you this correlation in nature, you could have won this game with 100% probability, but this kind of correlation discovered by Popescu-Ehrlich, this thesis thinks that it will not exist. And this correlation can be actually expressed in some binary form in this way. Yeah. Now I will tell you that, so maybe I have some other 10 minutes. Yeah. So this Bell's inequality we have derived by assuming that there is a more deeper theory than quantum mechanics, which we call hidden variable theory. But interestingly, Bell's inequality in 2005 by these people Anderson, they actually derived Bell's inequality. No, even before that, 1984, it was derived not by putting any condition on hidden variable, but on the observational probability. That means probability that we can collect from lab. Now, one derivation by these people, Anderson et al. In 2005, these two conditions, so there are two possible measurements on Alice's side, two possible measurement results on Bob's side, measurements on Bob's side, and again measurement results can be either +1 or -1. Now let us assume that one of the pair, either A1, A2 or B1, A2 are not jointly measurable. Like you know, position and momentum in quantum mechanics cannot be measured perfectly. There is no perfect joint measurement of position and momentum. Similarly, there is no perfect joint measurement of sigma x and sigma z. So you assume that at least one of the pair cannot be measured. Oh no, you are assuming in the contrary, one of the pair is jointly measurable. It may be either A1, A2 or B1, B2, but one of the pair is jointly measurable. That is your assumption. And second assumption is these theories satisfy no signaling conditions. Based on these two, there is no hidden variable theory. You just put these two conditions on this probability set, and you have Bell's inequality. So now the question is, we know already that these three people got Nobel Prize because they could prove in experiments that Bell's inequality is violated, and violation can reach up to 2√2 as we saw. So now the question is, if under these two conditions Bell's inequality can be derived and in practice Bell's inequality is violated, what conclusion we can make? So theory satisfies no signaling condition, and we know that quantum mechanics does not. Quantum mechanics indeed respects relativity condition or no signaling conditions. Then if Bell's inequality is violated, what has to be rejected? First one, there cannot be joint measurement. There cannot be two pair of observable cannot be jointly measured if Bell's inequality is violated. So if violation of Bell's inequality is established, then at the same time you establish that the pair of measurement that has been used to show that violation, they cannot be jointly measured. This is very profound thing that you can recover from violation of Bell's inequality. Yeah. And in 2009 there is a profound result. If a pair of observables, say A1, A2 are incompatible in quantum mechanics, that means they cannot be jointly measured, then there will be always violation of Bell's inequality. That means you can choose another particle and choose a particular state and two observable on this side, two observable on the other side, such that Bell's inequality is violated. And now this is very profound consequence. If two observable that in quantum mechanics you choose, if for them you get violation of Bell's inequality, then you can make a very strong comment. Maybe in future quantum mechanics may be replaced by some other theory, but these two observables which can be performed in practice, they will remain incompatible even in future theory. So they are incompatible by nature, not by a particular theory, because from the statistics you are telling that it is not possible. This is very profound. And third thing that we could derive from this Anderson's thing, myself, Manik and Shivashish and some other guy, that we could prove that maximum amount that this Bell quantity can achieve is 2√2. It cannot go beyond 2√2. In quantum mechanics, of course. I think I have finished my time, no? Yeah, I'll make just 2 comments. Yeah. Deriving Bell's inequality for operational theory too, there is another derivation of Bell's inequality. It tells, so first there is a definition, and operational theory is predictable. Now we are not going to deeper level, lambda level. It is again on the surface level. So an operational theory is predictable. I am not telling operational theory is deterministic. I am not telling it. Predictable if all these probabilities are either 0 or 1. You are talking about probabilities that you collect the statistics from measurement in lab, and from there you are collecting, you are constructing the statistics. So you are assuming that this probabilities is either 0 or 1, where k is the state of this theory, and it satisfies no signaling condition. That means probability of a particular result on one side does not depend on the choice of the measurement on the other side. Then this predictability and no signaling, it also implies no violation of Bell's inequality. This was discovered by Cavalcanti, Weismann in 2012. And you know, quantum mechanics satisfies no signaling condition. So what conclusion you can make because Bell's inequality is violated? So quantum mechanics violates Bell's inequality. So now you can, because the Bell's inequality has been derived under these 2 conditions, and quantum mechanics satisfies no signaling condition, you come to the conclusion unpredictability must be a fundamental feature of quantum mechanics. So in effect you get randomness, because these probabilities cannot be only 0 and 1, or either 0, only 0 and 1. And when the measurements that are involved in finding violation of Bell's inequalities, they must be unpredictable. That means there will be elements of randomness in their measurement results. And if Bell's inequality is violated by this amount b, which can be 2, which can be 2 root 2, which can be 4. So there is a particular way to calculate this nature paper from Spironio et al. So so you can calculate guessing probability. Guessing probability means you are trying to guess best guess, and best guess is this, where this b is the amount of Bell violation. And if you put b is equal to 4, b is equal to 4, when you get b is equal to 4? For an unphysical correlation like this. So when you put b is equal to 4, you get complete randomness. But for quantum mechanics, you know b is equal to 2 root 2. So if you put b is equal to 2 root 2, you don't get complete randomness, but 20% randomness from violation of Bell's inequality. But you know that when b is equal to 2 root 2 for quantum mechanics, it comes from a single state or maximally entangled state. And if you believe in quantum mechanics, then of course it is completely random, because local random matrix is identity by 2. Whatever you measure on this marginal density matrix, the results are completely random. But if you don't believe in quantum mechanics, you only believe in statistics, then from violation of Bell's inequality by the amount 2 root 2, you get only 20% device independent randomness. This is device independent randomness. You are not assuming that quantum mechanics is correct. You collect the statistics, from that you are telling there must be some randomness, then randomness is 20%. And second thing, I can have elaborate discussion in our discussion session that comes last. There we can discuss more elaborately. And let me finish by telling that you get also device independent secrecy from quantum mechanics. So already you have seen that this peer correlation, it is just a correlation. I am not talking about any theory like quantum theory. I am not talking about a state, observables, all these things. It is just a correlation. And this correlation is a very peculiar property. It cannot be correlated with the rest of the world. It is completely, if you have this, you don't have this correlation, but mathematically you can show that this correlation is completely monogamous. It cannot be correlated with the rest of the world. And if you have this correlation, you have secret key which is device independent. Because how key can be generated? They will measure, and after that they will discuss their measurements, not the result but the measurement. And when they both choose A2 and B2, one of them should flip his result. Then their results will be completely correlated and it will be secret key. Now, quantum mechanics, for quantum mechanics, so you have complete secrecy from PR correlation. Now you weaken PR correlation by some noise, and even up to some level, still you get secret key. And when you weaken this PR correlation, then at some point of time you will get the correlation from quantum mechanics, and you can say that you can get device independent key from quantum correlations. And so these are the conclusion, and yeah, I have finished. Thank you.
Thank you for the wonderful talk. The session is open for questions, comments.
All these arguments, are they consistent with relativity theory?
Yeah, relativity means I am taking this principle that velocity of light in vacuum, that is the final velocity. So here we are not using any particular value, but no signaling condition. That means you cannot instantaneously send some information or something instantaneously.
No, because you are having two places
Yeah.
separated by light years away in
Yeah.
your thing, which means
To assure that,
you have a finite distance between them,
Yeah.
very large. Supposing you travel in a frame which is traveling very high velocity, will they see the changes in the arguments?
no, that is a different question, because you are telling that whether from a different frame they will say the same results. Most possibly these values. So Alice measures and gets some values. Say I don't think that there is some other frame where someone will see it is down value. That I don't believe. But there may be some other things which may change.
Because finally tied up to locality, locality should come with some scale, right? How far the two things are.
So only you have to assure, to perform well measurement, you have to assure that the two event, measurement and getting result, these are space-like.
Space-like.
That you have to assure to get rid of the locality loophole condition. That's how measurements are challenging.
Okay.
Yeah, you talked about the result of von Neumann. So von Neumann's result.
Yeah.
So can you comment on that? Like finally, like what is the status of that? Should I think that von Neumann's result is wrong, or?
So of course von Neumann is wrong in that, because he put the second condition which should not be put in that way. But yeah, silly. So von Neumann, you forget about it, because he thought that this mathematical theorem will tell me the final results. So Einstein used to think in a way that a physicist should think. But Einstein is also wrong, because he not only believed in reality, he also believed in locality. So if you take the conjunction of reality and locality, then quantum mechanics revolves.
Is there any new proof later? Is there any statement after this, like later, like von Neumann corrected himself, or is there any progress after that?
I don't know when he died. Which year he died?
1950. I think he actually died before.
Yeah.
I see.
But Bell is still very confident. So it is like integration of fx dx is equal to 0 implies fx is equal to 0. So actually, if someone could tell von Neumann at that time that you are doing this thing, then then von Neumann could have immediately understood. Because it's not coming in that way, it's coming in a very roundabout way. So he could not see the faults in his proof.
The assumption is wrong, right?
Yeah, that assumption is wrong. Otherwise, as a mathematical theorem, it is perfect. So, as a mathematical theorem, it is linear functional, assumption of linear functional. So that is completely correct.
Sorry, did you at some point say Cyrilson's bound has been proven positively?
No, let me tell you that again you have to prove some principle, then only you can prove.
I see. Because I saw in the media and informal conversations that this reset MIP star equals RE proof implies that Cyrilson's bound is false. Is that, so what condition do you need to put to prove it?
So it is called information causality conditions.
I see.
It is some other version of no signaling condition.
I see.
More involved conditions. If you put that condition, then it can be shown that that condition will be violated if Bell quantity goes beyond 2 root 2.
Okay, thank you.
And there are some other conditions which exactly could not prove that if it goes to 2 plus epsilon, something like that, then yeah.
Okay, so if there are no further questions, let's thank the speaker again. I want to make one announcement. We can take 20 minutes for short break, for snacks and coffee, tea, and then come back at I think 11:40.
just one announcement.
Yeah.
So whoever now wants to do the registration, you have not yet done, you can go to the reception and do the registration. Okay, this is number one. And number two, in this ID card, in the back side there is this username and password. If you open IMSC website, you can use this thing with this username and password. Okay, thank you.
Okay, so let's move on to the next talk in the first half of the day. So next speaker is Professor S. Chaturvedi. He's going to talk about, I think it's a long title, I think you'll hear more about it actually. What's the time now?
Yeah,
55 minutes. 55 minutes. I'll be there. 1 minute.
you want help?
No, no. I'll manage. I'm really very happy to be back in math science on this occasion of celebration of the 100 years of quantum mechanics. Very thankful to the organizers to have considered me worthy of presenting something here, something in which I've been involved for a long time. And I have chosen to speak on this particular topic largely because, in fact, a very important contribution to this subject. There have been many contributions from Indian physicists to the subject of geometric phase, but the final word or the final picture, as I would try to outline in the historical perspective on this topic in the next slide, came from this institute, the work of Professor Mukunda and Simon, which is after many attempts at sort of understanding this notion of geometric phase, which came from the work of Michael Berry in 1984. There were several other works which tried to understand and extend and generalize this notion, but the final word eventually came from the work of Professor Mukunda and R. Simon from this institute. And I'm convinced that if there is at some stage in future, which would be probably in 2063, that one would be celebrating the 100th anniversary of this institute, these two papers, particularly this understanding of the geometric phase, as well as the work on entanglement in Gaussian states by Professor Simon, would certainly find a very distinctive position in that meeting. These are works which have, which would last a long time. They have a certain lasting quality about them. So let me just give you a brief historical development of this subject in order to put the work of which I'm going to follow up and talk about later in a proper perspective. So it started with a paper by Michael Berry in 1984 in the context of evolution of a time-dependent system. The Hamiltonian is time-dependent in the adiabatic approximation, which you would have learned in basic courses in quantum mechanics. And he came up with he found that if the Hamiltonian starts at t equal to 0 and comes back to its original form at some time capital T, then
during this evolution, adiabatic cyclic evolution, one finds that there is a phase which has purely geometric in character. In what sense it is geometric, we will come to in a minute. Then it was soon after Berry's paper, Ramasheshan and Nityananda pointed out that a similar kind of a phase was discovered in the context of polarization optics, interference in of polarization, polarized light beams, and this was in 1956, and which was also very similar to the kind of one found that the result of the work done by Michael Berry in the context of a two-level system were quite analogous to, were in fact identical to what Pancharatnam had found in the context of polarization interference in the context of polarization optics. This was then followed by Aranov and Anandan, who weakened the requirement of adiabatic evolution, but showed that such a phase emerges in the context of any cyclic evolution of a quantum system. And I think the major understanding of or the significance of this work of this geometric phase relating to the structure of the Hilbert space in quantum mechanics came from the work of Samuel and Bhandari in 1988. And then at that time I was in this institute, and we had heard about this geometric phase, and the example that Berry had considered was that of a two-level system in which the Berry phase also turns out to have a very nice another geometrical feature, namely it is the sort of, I will explain these words in a minute, but it had the meaning of the solid angle subtended by the curve in the state space at the origin. And it was then also, one talked about some kind of one could picture it as some kind of the analogy that was given was as if there is a monopole sitting at the center of the state space, and a very similar kind of a structure that emerges in this present context. So we, myself, Sri Ram and Srinivasan, were sort of confused, or at that time there was no clarity. Somebody had come and said, had heard E.C.G. Sudarshan talk about Berry phase in some other institute, and we started looking at this question, and what was puzzling us was, is it always that you have the interpretation of the Berry geometric phase as some kind of angle subtended by the curve at the origin of the state space or the parameter space? So we looked at a continuous variable example, a very simple one, namely that of a coherent state being taken around a circle in the complex plane, which describes where each point in the complex plane corresponds to a definite coherent state. And we found that in this present context, the geometric phase turns out to be, and we of course followed whatever prescription was given by Michael Berry, and found that in this case it turns out to be the area subtended by the circuit in the parameter space, which in this case turns out to be the complex plane, each complex variable corresponding to a given coherent state. And so it wasn't any sort of, again, it was nice, because now we felt that the interpretation of the value that you get of the phase associated with a curve need not always be some kind of a solid angle subtended at the origin. Let me tell you that these were early times, and we were also beginning to learn about these things. And it is at that time that we learned something new, mathematical notions like holonomy, etc., and took us a while to understand. With the help of other more mathematically educated people in the institute, we learnt about these notions and connection and holonomy and so on, which are now very commonly understood by most students. So this was one example where one could also connect it with a similar kind of an idea developed by Hannay, a collaborator of Michael Berry, in a purely classical context, where you're simply working with Hamiltonian description of the classical mechanical system, and you assume kind of an adiabatic evolution of the system under consideration in a closed curve. And one could show that the Berry phase connects to the Hannay angle in a classical setting the way it should be as given by as given in Hannay's paper. Then in 1993, Mukunda and Simon published a fairly large paper in Annals of Physics 228, page 205, fairly large paper, and this was the work which gave the complete the complete formulation, in my opinion, of the notion of geometric phase. And for the first time they brought out the direct connection between the Hilbert space structure of quantum mechanics and this notion of the geometric phase, and I will come to that in a little later. And in this paper also they connected this geometric phase, made a connection between the geometric phase which is associated with a curve in the state space with an object which is called the Bargmann invariant. And these Bargmann invariants appear in the context of, were introduced by Bargmann in the proof of Wigner's unitary anti-unitary theorem. Mukunda was aware of these, and surprisingly, when I was in TIFR, I had done a project with Mukunda and I had gone through this Wigner's theorem and learned about Bargmann invariants, which so many years later we had found very useful application in the context of Berry phase. So it's often things that you learned years earlier come back to you in some form or another in a different context and prove to be very useful. Then of course this was followed up, the connection between Bargmann invariants and the geometric phase was followed up by Mukunda and Simon and others. We have also some collaborative papers on it which are listed here. In particular, the last one, for instance, gives kind of a more, anyway, it's couched in a more mathematical language, but this notion of geometric phase, connection between geometric phase and the Bargmann invariants, and the notion of null phase curves were introduced by essentially by Mukunda and Simon in these papers, and this is what I'm going to outline in the lecture, in today's lecture. And then towards the end I would talk about null phase curves and some work that I have done in collaboration with a master's student at IISER Bhopal. Some very preliminary results, but what I would like to emphasize to you in this, to the young students, is that there are many questions still to be looked at, in particular in the context of null phase curves, which I think some of you might like to take them up. It's some mathematical as well as sort of those who have got good computational skills, how to actually come to grips with these null phase curves, particularly if you're dealing with higher dimensional systems, higher than 2. So I start with, having been a teacher all my life, I start with some very basic. I try to make things as complete as possible, if not over complete, but as complete as possible, so that even those who are not fully familiar or aware of what the discussion is about get something out of it. So as all of you know, that crucial feature of quantum mechanics is a Hilbert space, and I would, in this, just to set the notation right, we would denote elements of the Hilbert space by ket, psi, phi, and so on, and the scalar product would be written as shown. Now we define a structure related to this Hilbert space called the unit ball, which means it is a set of all states, normalized states in the Hilbert space. Of course, you must all be aware of the fact that the moment we go to the unit ball is not a vector space anymore. From the unit ball, we go to the ray space, or the state space as we call it in quantum mechanics, and the elements of the ray space are all vectors in the unit ball multiplied by a complex number of unit modulus. As you all know, there is a one-to-one correspondence between the elements of the ray space and the possible physical state of the quantum system, which are described by this Hilbert space. So again, to set the notation, I have drawn here the picture expressing the relation between the unit ball and the ray space. So the ray space is at the bottom, and at each point in the ray space there correspond infinitely many vectors in the unit ball, elements of the unit ball, which are related to each other by multiplication of by a phase factor. So this picture is crucial for the later development. So this is the connection between the state space or the ray space and the unit ball. Now, of course, two non-orthogonal, let us now ask the question of, there are so many phases because psi is we're dealing with a complex Hilbert space, and now what we want to do is to define what is meant by two vectors being in phase with each other, which will bring us to the concept which was a crucial part of Pancharatnam's work in the context of classical polarization optics. So two non-orthogonal vectors, psi1 and psi2, in the unit ball are said to be in phase if their scalar product is real and positive. Now again, sort of abstracting what Pancharatnam had done, which was inspired by the notion of interference in optics. The phase that came out of Pancharatnam's work, which is now referred to as the Pancharatnam phase, is what I've given here. We say that psi1 and psi2 are the Pancharatnam phase associated with any two non-orthogonal elements of the Hilbert space is given by the argument of this complex number, which is the overlap between the two vectors psi1 and psi2. Now, essentially what we are trying to do, as we will see, is to define this method allows you to ask a natural question, and that is, if I look at the vectors associated with the same point in the ray space, obviously there is a very clear meaning of what is the phase difference between the two vectors. But if I look at a vector at one point corresponding to one point in ray space, another point in the ray space, and ask the question, are they in phase or not? And this is the question which has no easy answer, because the overlap psi1, psi2 is a complex number. You don't know what phase you are talking about, and these these elements in the ball, on the unit ball, are located at different points, and we have to carefully define what is the meaning of these 2 points, whether they are in phase or not. And it is this Pancharatnam definition which comes in handy, and this is what we would mean by 2 vectors, 2 non-orthogonal vectors being the phase difference or the phase between psi1 and psi2, and this is the quantity that is given here. Now it turned out something which was also noticed by Pancharatnam, that this notion of being in phase is not transitive. That is to say, if psi1 and psi2 are in phase, psi2 and psi3 are in phase, then it does not mean that psi3 and psi1 are in phase. So this is not a transitive notion of being in phase is not transitive, and this is again, most of it is sort of borrowed from the works of Mukunda and Simon, the initial papers on this subject. So I'm just paraphrasing what has already been said, and this is where the Bargmann invariants come in. This non-transitivity of this notion of being in phase is best expressed through what is called a Bargmann invariant, whose definition is given here, which is the lowest order Bargmann invariant would be psi1, psi2, which is then will be psi1, psi2, psi2, psi1, which is simply will be the modulus square of the overlap between psi1 and psi2. The third order Bargmann invariant, which is relevant for expressing this non-transitivity of the being in phase in Pancharatnam sense, is captured by this third order Bargmann invariant. So if I have 3 vectors, psi1 and psi2, psi3, all of them pairwise non-orthogonal, then this is the definition of the third order Bargmann invariant. Now it turns out that you may define higher order Bargmann invariants, 4th order, 5th order, but all of them can be re-expressed in terms of the the Bargmann invariants of 2nd order and 3rd order. Of course, not in a linear fashion, but they can all be related. So these are very crucial. You may ask I may mention just as an aside that there was some work which I had done with Mukunda in the context of the Kabibo, Kobayashi, Maskawa matrix and parametrization of that matrix, and we found that in that context, 4th order Bargmann invariants appear in a very natural way in describing this, describing mixing matrices. So there are places where 4th order Bargmann invariants also play an important role. Now 2 important properties of this 3-vertex Bargmann invariant, and in fact is applicable to higher order ones as well, is their invariance under unitary transformations. That is, if you start from a vector psi j, apply a unitary transformation to go to another vector psi j prime, and you do it to all the elements in the triplet, then you find that the Bargmann invariant does not change in its value. Then a natural question to ask is, and this is something which is we pursued, myself, Mukunda, Akhilesh and Malesh in a paper which I will cite a little later. So most of the work that I'm going to present is now relates to that paper which was published maybe 4 years ago. So you may ask the question that for how many parameters does this third order algebraically independent parameters are required to characterize a Bargmann invariant? It turns out that for n greater than 2, there are 6 angle type parameters which are needed to algebraically independent parameters which are needed to specify delta 3. For n equal to 2, it turns out that the 6 are algebraic, only 5 out of 6 are algebraically independent. This is just some general information about third order Bargmann invariants. And now it turns out curiously that if you look at the infinite dimensional case in which the vector psi1, psi2 and psi3 are chosen to be coherent states, then it turns out that surprisingly, for reasons which one may speculate to be basically the overcompleteness of the coherent states, in this curious case what one finds is that you require, like n equal to 2 system, you only require 5 independent parameters to characterize delta 3. So psi1, psi2, psi3 are 3 coherent states, and of course as we know the coherent states psi1, z1, psi1 and psi2, psi3 is not can be expressed in terms of psi1 and psi2. Perhaps that is the reason which causes this reduction in the number of parameters required to specify a third order Bargmann invariant. Now next we move to the geometric phase as such, and let me just again set the notation. We can think of curves, and I will maybe move on to this picture. So the curves in the ray space are denoted by normal C, and the curves in the corresponding lifts, by a lift I mean the curves, smooth lifts, which curves in the unit ball which project to the same curve in the ray space. So I've given here examples of 2 curves which are lifts of this curve C12 shown in the ray space. So 2 different curves which project to the same curve in the ray space. So as you know, a curve is parameterized by, if you're starting with we would look at curves which have endpoints. At the endpoints you have 2 states, rho S1 and rho S2, and we are looking at smooth curves joining these 2 points with rho S1 and rho S2 as the endpoints. We will, for simplicity, or we will assume that these curves are piecewise once differentiable. So the terminology which I would use is a curve in the ray space and its lift. By that we mean any curve which has the same projection in the ray space. That would be the meaning of a lift and its projection. Now I come to the work of Simon and Mukunda, and that is the following: that a geometric phase, so geometric phases are associated with a curve in a curve, and you take any curve in the unit ball written by this cursive C12, and you can, there's an expression given here. The first term is the Pancharatnam phase, as we learnt earlier, and then there's an imaginary part of certain expression which goes by the name of Berry connection, and or also in the earlier literature as the dynamical phase. So this quantity on the left hand side, which is a difference of these 2 quantities, is called the geometric phase. It is geometric in the sense that you can choose any curve, that if you look at a curve in the ray space, and you look at any of its lift and you calculate this quantity has the same value for all the curves in the state space. So let me just make it very clear once more. So it is basically geometric at this stage in the sense that I have a curve in the state space and I look at its lift, say C12 or C12 prime, use this formula which is given in terms of elements of the, vectors in the, or elements of the unit ball. You calculate this quantity for any two lifts which have the same projection. The value you are going to get is the same, so it is a property of the curve in the state space. So this is the expression. Unlike the previous works that always dealt with closed curves, etc., Mukunda and Simon's work takes us far away from the assumptions that were originally made in the context of geometric phases to dealing with geometric phases associated with open curves as well, and this is the result. Now we come to move on to, I introduced the notion of a Bargmann invariant, which you may recall is not a function of a curve but 3 points in the unit ball. And now we would like to see what is the connection between the geometric phase that we have defined here and the Bargmann invariants. And in order to prepare you for, again, certain terminology that I'm going to use is the following, that if you take any two vectors, psi1 and psi2, and these are chosen to be in phase in the Pancharatnam sense, that is, it is equal to, their overlap is equal to cos theta 0 by 2, with theta 0 lying between 0 and pi. That is to say, psi1, psi2 overlap is real and positive. Then if I consider, I define a geodesic from psi1 to psi2 in the following sense, a parametrized curve in B, which starts at psi1 and psi2 and moves along this parametrized curve. So this is what I would mean by geodesic in the states in this context. And of course one can relate it to a natural metric on the quantum mechanical Hilbert space, which goes by the name of Fubini-Studi metric and so on. So they are geodesics with respect to that metric. But for the time being, you just assume that this is the shortest curve in some sense, joining psi1 and psi2 in the unit ball. Now, the geodesic in a ray space is of course obtained by, this is a curve in the unit ball, and you look at its projection and it will be denoted by this quantity C here, which is a projection of any geodesic that you can, of that geodesic onto the projection of that in the ray space. Now we define so this is the notion of a geodesic. Now we define, or was defined by Simon and Mukunda, and that is the notion of a null phase curve. And the significance of that will become clear in a minute. So if I have a null phase curve is defined in the following manner, that if I start with 2 points, psi1, S1 and S2 as the starting points, and then I consider all points lying between S1 and S2, S, S prime and S double prime, calculate this Bargmann invariant on these 3 points, and if it turns out that for any choice of S, S prime, S double prime on the curve, if this Bargmann invariant is real and positive, then we will say that this is a null phase curve. This is the definition of a null phase curve. Alternatively, one could say that you fix a point S naught on the curve and ask the question, and if it so happens that any 2 points S and S prime are in phase with the vector associated with the point S naught, then we say that this curve is a null phase curve. Essentially, if you like to picture it, you start from all along the curve. If you go from one point to the neighboring point, you are essentially choosing a point on that fiber to be in phase in the Pancharatnam sense. So let me go back in order to explain that idea. So if I start from this curve, start from the starting point, and then on the next fiber I have infinitely many choices, but I choose a vector which is in phase with the starting point in the Pancharatnam sense. And I keep doing this all along the curve, so then what I get is a null phase curve. So I've now defined geodesics and null phase curves, and it turns out that geodesics and for n equal to 2, geodesics and null phase curves they coincide, but in higher dimensions the null phase curves and geodesics are not the same. In fact, there are infinitely many null phase curves that you can define the moment you go to three-level quantum system. N equal to 2, a qubit, for example, the geodesics and the null phase curves are identical, but in higher dimensions these are not necessarily the same. And rest of what I have to say would focus on some understanding that one has got about these null phase curves. And what is the significance of these null phase curves, and what is the connection between the Bargmann invariants and the null phase curves? And that is the following, and this is the result again to be found in the works of Simon and Mukunda, and that is that if I consider 3 points, psi1, psi2, and I join psi1 and psi2 by a null phase curve called n12, then joins psi2 and psi3 by a null phase curve n23, and then join 3 and 1 by a null phase curve n31 to, I'll call it a triangle. So as to complete this triangle, then you get a curve, a closed curve, which is called capital N, and it turns out that the relation between the Bargmann invariant and this particular curve composed of these 3 null phase curves is exactly the relation is given here, that the geometric phase associated with such a triangle or a curve in the curve is equal to minus is a negative of the argument of the Bargmann invariant psi1, psi2, psi3. So understand this, psi1, psi2, psi3 are 3 points and with no reference to a curve, but if you join these 3 points by null phase curves, then you get a closed curve, and the geometric phase associated with this null phase curve is exactly equal to the argument of the Bargmann invariant, which is basically a 3-point function. So this is the crucial result, crucial connection between the geometric phase and the Bargmann invariant. For n equal to 2, for example, the ray space, as you all know, is given by the Poincare block sphere, and geodesics on which are parts of the great circles on the sphere are the parts are easily picturized, and one can, the original calculations by Berry were based on n equal to 2 level system, and what he found was again that if I take a 2 level system from a point, some point on the Poincare block sphere, take it along a closed curve in the Poincare block sphere, either through evolution or by changing certain parameters or whatever, and bring it back to the same point, then this geometric phase that was introduced by him acquires another geometric feature, namely it is given by the solid angle subtended by that curve at the origin. So the first sense in which I talked about a geometric phase was more in the sense of, was more related with the fact that it was only a function of the curve in the state space, and in the present context acquires another geometric feature, namely connection with half the solid angle subtended by the curve at the origin. Please, if you have any questions at any stage, you can ask me as we go along, if there is something that is not clear and requires repetition or more elaboration. So this was the result which was found by Berry in the context of a spin half particle subject to a magnetic field which was taken around a circle, and this was also the result that was found by Pancharatnam in the context of polarization optics. Now what I described earlier was a block description, Poincare block description for n equal to 2, but similar kind of description can be given for n level system, and by appropriate changes in the expression for an arbitrary element of the ray space, and that is given here. For example, for n equal to 3, instead of the Pauli matrices that appeared in that context, you have SU3 matrices, the Gell-Mann matrices, and the difficulty now is that the simplicity that one had in the n equal to 2 case is lost, because if you remember in the Poincare block description, the states are in one-to-one correspondence with unit vectors in three-dimensional real space. Here it turns out that again you have a correspondence between vectors in real vectors, but these vectors are 8-dimensional, and of course they are unit vectors, but in addition, in order to ensure the positivity of the of rho, which is positivity of the state, you have other restrictions on these vectors which are given here, and that makes the picturing the state space very complicated. There was one person called Sandeep Goel in this institute many years ago who was trying to sort of get a picture of the phase space for n equal to 3 systems, and it turns out that it's certainly not easy to visualize as it is for n equal to 2 case. So now what I would do is to try and this is some work which we did recently, and that is to try to make or at least develop a way in which we can picture these null phase curves and geodesics in higher dimensional systems in an easier way, because they cannot be pictured as easily as they can be for n equal to 2 systems. So now just one comment here and something which you all perhaps know, that so what we would like to basically do is somehow have a picture for say a 3-stage system, and to discuss geodesics and null phase curves in that context, we would like to have a picture similar to the Poincare block sphere as we have for n equal to 2. For that, one may notice that if I have a Hilbert space of n minus 1 particles, and I consider its each Hilbert space is 2-dimensional, and if I look at its symmetrized subspace of such a Hilbert space, then this exactly has the dimension n. So what we would like to do is exploit this connection. You may recall that if I have an m-stage system and I have n particles, then if I look at the symmetrized subspace, its dimension is given by the binomial coefficient m plus n minus 1 n, as you might have learnt in statistical mechanics. And now if you put capital N, capital M equal to 2, which is the number of states in which each particle can exist, then what you get is exactly this result. So if you have a d-level system, then you can describe it by d minus 1 qubits or 2-level systems, symmetrized subspace of d minus 1 systems. So if d is equal to 2, of course you have one Hilbert space of 2 dimension, 1 qubit. If you have d equal to 3, then you would be dealing with 2 qubits, but the symmetrized subspace of this Hilbert space. And as you know, you would have learnt in statistical mechanics that we can describe such symmetrized, give a Fock description for such states in terms of creation annihilation operators obeying the usual commutation, bosonic commutation relations. And so that is what we will choose. So the Hilbert space would now be basically this Fock space which I have written down here. And for an n-level system, it will be given by the possible basis in this Fock space is given here. So you see A1 dagger, A2 dagger acting on the no particle state. This gives you exactly n states, and they constitute an orthonormal basis in the symmetrized subspace that I have indicated here. Sorry?
How this dimension of the symmetrized subspace is scaled with n? So
say suppose I have here, as I have indicated, suppose I have, suppose you have n Hilbert spaces, each of dimension m.
Oh.
Huh? So m means the number of states the particle can take.
Yeah.
And if you symmetrize that n-fold tensor product, so let me make it clear. Capital N, number of particles, m are the number of single particle states in which each particle can exist. So I have an n-fold tensor product of Hilbert spaces, each of dimension m.
Oh.
And if I take a symmetrized subspace, then the dimension of the symmetrized subspace is given by both and m plus n minus 1 n. Now if I put this capital N, which is the number of capital M, which is the number of states, to be 2, then what I get is the binomial coefficient n plus 1 n. So I would n plus 1, if n plus 1 is equal to d, the quantum state I am interested in, so this capital N number of particles is given by d minus 1. So if I have d equal to 3, then symmetrized subspace of 2 qubits would be in one-to-one correspondence with the states of this 3-level system. Right? This is the key observation, and made by, not me, by Majorana. So this is the orthonormal basis in this Fock space. So any vector in our n-dimensional Hilbert's n-dimensional state n-state system can be represented in the Fock space by in this form, where all these coefficients all add up to 1. Now, crucial observation of Majorana was that any such state can be written in this product form. So, involving, you can factor any such state into this form, where alpha k and beta k are two-dimensional complex vectors. So, alpha k and beta k are numbers. K goes from 1 to n minus 1. Alpha k and beta k are complex numbers. And so you can imagine that now what we have done is come to a correspondence with the two-dimensional complex vectors whose entries are alpha k and beta k. So now I would have this, any vector can be written in this form, and so we have now made the connection between the block sphere that we had in the context of a two-dimensional system and the state space of an n-level system. Any question at this point? Anything that I have, you find confusing? Yes?
Is there any physical understanding of the curve which takes us from psi 1 to psi 2?
Which physical understanding?
Is it like unitary operation or?
Yes. If, for example, in the initial works that I quoted in the historical development, this parameter that I've called S is the time, and you are looking at a time evolution.
Okay.
So physically, but here in this entire formalism, there is no restriction on whether you are looking at Hamiltonian evolution, time evolution, or what is the origin of this curve. So that is the advancement that is made in this work by Mukunda and Simon. Then you take any curve, how it is generated, it doesn't matter. So it really makes a connection between basically the kinematics of quantum mechanics.
Yes.
That geometric phase, initially one had in a historical point of view, one had the idea that it is something to do with the evolution, adiabatic evolution, etc. But this work makes it a general feature of the Hilbert space structure of quantum mechanics rather than any association with time evolution.
But is there any restriction on this curve? This can also be some zigzag and you can go.
It can be anything you like,
I see.
as long as it is piecewise continuous and smooth in some sense. Apart from those automatic requirements which we make in physics about curves.
Okay, thank you.
Piecewise continuous and once differential. So now we have made this connection, that is if you look at this state here, which is describes an n-level system, little n-level system, then now we have, it can be represented by two-dimensional columns and k going from k taking on n values. So any general normalized vector in the n-dimensional system, quantum mechanical system, can be expressed in terms of these n two-dimensional column vectors. So we have now made the connection between states in the n-level system. Three-level system, for instance, would be associated with you've got this connection between this and two-dimensional column vectors. So this is the connection which was noted by Majorana and goes by the name of Majorana construction. With each of these complex numbers that appear in the Majorana expression, we can associate a unit vector in this manner, and so now we have got the required connection in order to describe a state in an n-level system through n minus 1 qubits. So now we can imagine curves, and we would like to see what do the curves for the n-level system look like in this Majorana picture. Let me just make some comments here that this structure can easily be identified with, if you have redefined this n to be 2j plus 1 and k then as j minus 1, then you can rewrite that vector in this following form, which we have come across in the context of spin j system, where m takes on values minus j2 plus j. And if you take a direct sum of all such spaces which give you a spin j representation of SU2, then what you are led to is a Hilbert space, which we call, for reasons other than what is relevant here, we call it a Schwinger representation, because this representation contains all representations of SU2 exactly once, and mathematically this is referred to as a model representation for SU2. So this is the connection between the block, the Majorana description and the Schwinger basis for SU2. Right. Now let me just state some interesting results. We want to make a connection between remember that these psi1, psi2, psi3 are states in an n-dimensional n-level system, and these we can calculate, and delta 3 is the Bargmann invariant associated with this, and the argument of this re-expressed in terms of the block description that is made available by the Majorana representation is this. Now it turns out that using the SU2 action and the unitary invariance under U2 unitary operations, these vectors that appear in the Majorana description, if I take 3 points, then I can always choose the first one to have the structure 1, 0. This again to be a single vector, and this psi k prime then would be represented by actually 2 points on the block sphere. I'll come to that in a minute. So a general n-level system geometric phase associated with a 3-vertex Bargmann invariant is a sum of these n-1 geometric phases associated with the corresponding 3-vertex Bargmann invariants on the Poincare block sphere. So this is the connection, and this makes it possible for us to look at geodesics and, for instance, geodesics and null phase curves in 3-level systems. We can picture them on Poincare block sphere. So let me just make some comments here that geodesics of n-level quantum systems, now we will come to some general results, and I'll show you pictures a little later. One may ask the question, let me now leave the slide. Suppose I have a 3-level system. I have a notion of a geodesic as I've already defined, and for this 3-level system I look at what does this, I would require 2 symmetrized subspace of 2 qubits. So each point each vector in the 3-level system would now be represented by 2 points in general on the block sphere. So it may happen that the 2 points are degenerate, it may happen that the 2 points are, depending on what your vector is, or it may happen that the 2 points, the state is represented by 2 points. Now I ask the question that if I have a geodesic in the n level system, what does it look like? So points, the picture is clear. Now if I have a curve in n equal to 3 system, a geodesic for example, what does it look like in the context, in the block picture as made available by the Majorana construction. So is the question clear? So this is, yes. That is correct.
Then there are Majorana polynomials appear there. Majorana polynomials.
Yes.
So do they come in your invariance?
That's right. Majorana polynomial are basically, these coefficients that I talked about, these coefficients that are given here, and that they can be factorized in this form. So this set of coefficients that appear here, so Ck, Xk, they will be called the Majorana polynomial, and Majorana showed that that polynomial can be factorized in this way.
Thank you.
That is the idea. Yes. Any other question? So now we may ask, suppose I consider a geodesic on an n equal to 3 system or n level system, what will be its corresponding picture in this block, Poincare block picture that we have just developed. There are some general results which I will indicate through photo pictures in a minute, and this is some work by Mittal, Akhilesh and Sandeep K. Goel. So the result is the following. Geodesics of an n-level quantum system decompose into n-1 circular segments on the block sphere, not geodesics but circular segments on the block sphere where the n points are represented by n-1 fold degenerate points on the Poincare block sphere. When n is odd, so this is some general result that these people have been able to show. I won't go into the details because details are going to be somewhat technical, but we have a very comprehensive answer to this question as far as geodesics are concerned. What do they look like in the Majorana representation? So this is the picture, and I will show you numerical computational pictures of this in a minute. So what I'm trying to say is that here there are many questions which one needs to answer, and how do the curves in the n-level system, what do they look like in the context of now geodesics, of course you can answer this question, but we would like to go beyond and ask the question, what about null phase curves? What do they look like when you translate them into the block picture in the Majorana formulation? So for example, if I have n equal to 3 and I take two states, psi1 and psi2, and I assume that both are degenerate, that is, both are represented by 1 point on the Poincare block sphere, then this is the picture that you get. That the geodesic in n equal to 3 space can now be pictured by these curves on the Poincare block sphere. So this is the situation when the two vectors psi1 and psi2 are degenerate. That is, they are represented by the same point on the Poincare block sphere. Now moving on to a situation where n equal to 3, where psi1 and psi2 are both non-degenerate. So now this vector psi1 will be represented by 2 points, and so would the vector psi2 be represented by 2 points on this sphere. And then if you look at the geodesic joining psi1 and psi2 for this n equal to 3 system and look at its image in the Poincare block picture, then this is what you get. This is again consistent with, I'm just showing you an example of the result which was stated in the previous slide. And suppose if you have a situation where one is degenerate and psi2, so there's 1 point here, one vector psi1 which is degenerate, which is represented by 1 point here, psi2 is non-degenerate, so it is represented by 2 points on the Poincare block sphere. And if you look at, this is the picture of the geodesic joining psi1 and psi2 for an n equal to 3 system. Now, then these people also go on to look at special classes of null phase curves. So remember what I said, the geodesic is of course given uniquely for any n-level system, but null phase curves are infinitely many of them. And the results that we quoted, the connection between the Bargmann invariants and the null phase curves applies to any null phase curve that you may choose to join psi1, psi2, 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 and psi2, psi1, psi2, psi2, psi3, and psi3, psi1. Now you have to, there are infinitely many of these null phase curves, and you have to, and this is again another question, that can one think of suitable classes or distinct classes of null phase curves? Can one divide this set of all null phase curves into equivalent, similar classes by in that way? And this is a special class. I won't go into the details because that will take us too far. They have given a class of null phase curves with specific properties, and they have studied them, and I will show you a picture. This is n equal to 3, and you take a null phase curve in that class joining psi2 and psi2, which are both degenerate. Then of course you get these two curves joining these 2 points, and the properties one would like to see. What can one say about the images of the curves that you get in the Poincare block description for the chosen class of null phase curves? And again, another example where psi1 and psi2 are both degenerate, and one has chosen a null phase curve from the given chosen class that I just mentioned, and you find that they have this kind of an image in the Majorana description. Now, there is also some experimental work on this by Tamate, Ogawa, Kitano and that group, and what they find is that if you, this is an experimental work involving polarization states of light, and what they find is that if you look at the 3-vertex Bargmann invariant for n equal to 3, and then what you find that and if you vary some of these parameters characterizing the experimental arrangement, then you find that the argument of the Bargmann invariant goes these discontinuous jumps or has this sort of a behavior, and they suggest that it might be of some use in designing switches, etc. So what one is talking about has some applications. In their context, what they were looking at is basically the geodesic curves. This student of mine, Piyush Verma, who did a BSMS thesis in 2024, has developed a way of generating these null phase curves purely numerically. Remember that the null phase curves that I had defined requires you to satisfy conditions of 2 points being in phase with respect to S0 for all points on the curve. It's very difficult to do it. There's a construction that is given in our paper, which I mentioned earlier, how to construct these null phase curves, and he's used that use the computer to generate such null phase curves, and he's been able to show that as you go to higher dimensional systems, he has investigated these jumps that were studied by this Japanese group. So I have essentially come to an end of what I had to say, and I hope I have tried to bring out, first of all, the significance and importance of the work that was done here. In the context of 100 years, I mean, it is a feature of the Hilbert space structure of quantum mechanics, and a very fundamental work, and complete answers were given through the work of Mukunda and Simon, and I'm sure that this a very important contribution that has come from this institute. And as I've tried to indicate to you, that those of you who are mathematically minded may also find some interesting questions that can be asked in the context of null phase curves in n equal to 3, 4, 5 dimensions, classes of null phase curves that one can think of, and look at their pictures in the Majorana-Schwinger representation. I think I will stop here.
Thank you very much. Questions, comments?
Thank you for the nice talk. So when you talk about this invariant, Bergman invariant, is it the unitary invariant that you are talking about only?
They are basically quantities. Let me just show you this. So these are, if you have psi 1, psi 2, psi 3, then delta 3, it's a function only of the associated points rho 1, rho 2, rho 3 in the ray space. So
Okay.
psi 1, psi 2, psi 3, if you change, let me use the word gauge transformation, that is, you multiply each vector by an arbitrary phase factor to the second one, an arbitrary phase factor to the third one, this quantity remains unchanged. So it is a ray space quantity.
I see, okay. So, so how does one, if I don't know in which context it will be necessary, how does one look for generalizing it for mixed state case? This is already in pure state
The
case.
question of mixed states, geometric phases in the context of mixed states is somehow, I don't know, I have not followed up the literature, but initially, until the time that I was following this question of mixed state entanglement, mixed state geometric phases associated with mixed states, we had a picture, and that was the following. As you all know that a mixed state can be written as a convex combination of pure states in infinitely many ways. So if I want to define a geometric phase associated with a mixed state, one natural procedure would be, I know how to compute geometric phases for pure states, and I would now calculate the geometric phase associated with each of the pure states that appear in this decomposition and average it over the probabilities that appear in this decomposition. But as you know that a given mixed state can be expressed in terms of pure states in infinitely many ways. So you are lost because then you would have to calculate it over all such decompositions and then find the extrema of these in order to be able to define notion of a mixed state, much the same way as one defines entanglement in the context of mixed states. So it's a difficult, that is one way. And at some stage we felt that as far as the geometric phase is concerned, and we had some reasons to believe, and we wrote a paper on that as well, that for geometric phase the best thing to do would be to decompose, to take the decomposition of rho in its eigenbasis. That is in terms of the projectors associated with its eigenvectors. That has some special role in the context of mixed states. And then you average it over, consider some sort of an average over the decomposition in the spectral decomposition of the density matrix. We had reasons to believe that that has a special role. But later on, there are a lot of people, particularly Arun Pati and Sjöqvist in Sweden, they have come up with definitions of geometric phase for mixed states as well. I have not studied that subject very.
I was thinking whether this optimization will be made for a spectral. It may happen.
For what we felt or what I tried but gave up in the way because it required a lot of numerical computational work with which I have no familiarity. But the idea was that if I look at, for instance, take this point of view, decomposition of the mixed state in terms of pure states, and for each of the pure state I know how to calculate the geometric phase, and then average it over the decomposition. I wanted to see whether the spectral decomposition has any special role, but I could not proceed further because of lack of computational skills.
Something which I haven't understood correctly. So, so you talked about this geometric phase written as some combination of Pancharatnam phase and Berry phase, right?
That's correct.
So we know that in Berry phase, at the end of the process, there will be some remnant from about the physics that happened, right? About this Berry phase, right?
No, see,
it's not just.
So if you want to connect it with Berry's work, then the curve that you choose is the one that is obtained by evolution of the. So Mukunda and Simon's work subsumes all previous works and gives it a purely a kinematic meaning, purely an aspect of the complex Hilbert space associated with a quantum mechanical system. No dynamics. If the curve could be generated by evolution.
Yeah, so I'm just trying to ask, you consider the sum of Pancharatnam phase and the Berry phase, or the difference. It's mainly to take away the phase that is coming from the unitary transformation, right?
Right.
So other than that, whether Pancharatnam phase has anything more non-trivial in it, like the Berry phase, there's something which I want to understand.
Can you repeat the question?
Yeah, so the Pancharatnam phase, I want to know whether there is a physics within that phase, or is it just that it is just capturing the phase coming from the unitary transformation?
No, there is, as far as Pancharatnam, after all, the problem is the following. You have these two points in the ray space, and you have infinitely many elements associated with those 2 points. These are complex vectors, complex elements of the. Now you calculate you want to say what is the meaning of this and this being in phase. If there are points on the same fiber, then of course the phase difference notion of phase difference is natural. But if these are located at different points, the situation is very similar to taking a vector on a sphere, for instance, and the notion of transporting this vector, parallel transport of this vector along a curve. You give a definition of this connection or this rule of parallel transport, then you can say whether a vector here and a vector at a different point are in phase or not. So that's it is in the similar spirit.
Okay, thank you.
And Pancharatnam's idea was rooted in a very physics. We were looking at interference between polarization optics. So the two-dimensional columns that we are dealing with are electric fields. And he asked the question, when would they be in phase? In the optical sense, that is, when would the interference pattern be connected with the interference? So it was I suppose one could alter the definition of being in phase and come up with a new definition, but this is the one that in some sense subsumes all other previous works which had some association with dynamical evolution and so on. This takes you away from that, and also talks about, also defines you the geometric phase between 2 points in ray space, 2 vectors in a unit ball, which, and you don't have to talk about closed curves anymore.
You discussed n-particle bosonic totally symmetric states. Could you please comment about what happens if you take fermionic and take totally?
Where are you? Yes.
Yeah, could you comment about what happens when you take fermionic totally antisymmetric states? Any of these results follow through or they differ completely?
No, because in the fermionic case, suppose I think the connection with, so in the case of fermions, you would have as the, suppose you have n particles, capital N particles, and m states. Then elementary statistical mechanics tells us that total number of the dimension of the anti-symmetrized subspace is capital Mn. Now, suppose I wanted this to be equal to D. Now, in this case, it turns out, in the bosonic case, the formula is such that if I put capital N equal to 2, that is 2 states, then I have Dn plus 1 n, and that is equal to n. So if I have a d-dimensional system, then d minus 1 qubits, symmetrized subspace of d min 2 qubits, that will work. And 2 qubits, we have a description given by Poincare block sphere. For fermions, there would be no such connection. Capital M, suppose you have you want to M, you put M to be equal to n plus 1. Then you have n plus 1 equal to D. So n equal to D. So if number of fermions, the number of states that you would require would be D minus 1. So I don't think there'll be. See here, Ramesh, the important thing was to connect it with two-dimensional Hilbert spaces where you have a good Poincare block description, which would not be possible in the case of fermions.
So I would like to understand the plot that you showed.
Yes.
Where you had phi along the x-axis.
Yes.
I was not quite sure what is the y-axis and what exactly is phi there.
Here.
So I think you had one plot where.
Just 1 second.
Yeah,
Yes,
this
here.
one, yeah.
Here one is calculating the argument of the, now what will, I have here I have got 4 points. So I'm looking at n equal to 3 system. So and I'm assuming that one of them is degenerate, so 1, and then I would have 2 points corresponding to the second one, another 2 points corresponding to the other 2. Now I can draw 2 geodesic triangles on it and calculate, what they do is calculate and there are these various parameters which basically describe the orientation or the position of these geodesic triangles. And experimentally they change these parameters. So one of them is this angle phi. This angle phi is here. I can't read
Which
it.
is characterizing one of the states, or is it some combined?
Eh?
Is it characterizing one of the sides?
You start with one state.
Okay.
Now you change the experimental parameters so that the one state moves.
I see.
One state moves and you take it round and come back, and then you find that the point where it goes crosses that, you have a discontinuity, and then the same pattern repeats.
And what is the y-axis?
Y-axis is this Bachmann phase.
I see. It's not invariant under this phi change.
No, because you're changing the psi 1, psi 2, psi 3, no?
I see.
If you had a fixed psi 1, psi 2, so one of them you change depending on the one experimental parameter, and then you study how the Bachmann invariant Bachmann phase changes associated with these 3 states.
Okay, thank you.
That is it.
So we are running out of time, so let's close the session by thanking both the speakers.
So we are supposed to come back at 2 o'clock.